This is how to do problem 141 from chapter 9. The full problem will be in the description, but for now, determine the heat loss by the radiation by taking the emissivity of the collector surface to be 0.85 and the effective sky temperature to be negative 15 degrees Celsius. So let's write down the givens, that is like in the rest of the question. We have L equals 4.5 meters, width 1.5 meters, surface temperature 42 degrees Celsius, T infinity 8 degrees Celsius, and the temperature of the sky, which I read aloud, negative 15 degrees Celsius, and the emissivity, which I also read aloud, 0.85. And we need to find Q convection and Q radiation. Okay, so first let's find the surface area, which is length times width. It's easy. 4.5 times 1.5 is 6.75 meters squared. Next we find TF equals TS plus T infinity divided by 2. Plug it in, it's 42 plus 8 divided by 2, and you get 25 degrees Celsius. Next, we use that temperature to find properties on the table. K equals 0.02551, Prandtl number 0.7296. And then let's continue with the rest of the properties. Times 10 to the negative 5 meters squared per second. Sigma is 5.67 times 10 to negative 8 per meter squared fourth. Okay. Now we have those. We will continue to calculate the volume expansion coefficient, which is denoted by beta, and we can do 1 over TF, and that's 1 over 298. That's in Kelvin, so we add the necessary things. So then we get 3.36 times 10 to the negative 3. And of course it's inverse Kelvin. Next, we find the characteristic length, and we get surface area by that, and we get we calculated the surface area earlier to be 6.75, so you get 6.75, and then we get, this is the perimeter, so it's 2 times 1.5 plus 4.5, and of course it's because it's a flat plate solar collector, so it's like a rectangular perimeter. So after that we get 0.5625 meters for the characteristic length. Next, we calculate the Raleigh's number, and that is minus T infinity. Characteristic length cubed squared Prandtl number. Alright. Now this G is gravity, so 9.81. This beta we calculated at 3.36 times 10 to the negative 3. TS was 42. T infinity was 8. This characteristic length we just calculated 0.5625 cubed. The Prandtl number you get from the table. Now it looks like I may not have room for it, but we'll squeeze it in. 7296 and divided by, and we have that here, 1.562 times 10 to the negative 5. Plug that into the calculator and we get 5.96 times 10 to the 8. So that's our Raleigh's number. Next, we find the Nusselt number. And that equals 0.15 times the Raleigh's number cubed root. So, plug that in, 0.15 times 5.96 times 10 to the 8, and then we find the cubic root of that, and we get 126.23. Next we find H, and that just equals you might not find the equation like this, but this is after some algebra. But it's real simple algebra, so don't worry about it. 0.02551. This is just plugging it in. That's the K value divided by the characteristic length, which we calculated to be 0.5625. Then our Nusselt number, which is 126.23. Right? After that, we get 5.7246 degrees Celsius. So here's our H coefficient. Now we have this, we can calculate our Q convection, and that would just be H ASTS minus T infinity, right? So the H was 5.7246, and the surface area was 6.75, and then we got 42 minus 8, and that equals 1313.79. So that's the answer to the first part. Next we can calculate the Q radiation, and that's where we use the emissivity coefficient, surface, that sigma from the table, property tables that we got. I can flip the paper over so you can see we got it from the right here. So, and then almost everything, we calculated that, and that was just in the problem statement. So 0.85, 6.75, and then we had the 5.67 times 10 to the negative 8. Here we gotta convert these to Kelvin. So we have 42 plus 273 to the power 4 minus, and here negative 15 plus 273 to the power of 4. And after plugging all that into the calculator, it's 1761.53. And that's that.